Good day, Math 10Cs. Today we're beginning our first lesson in Chapter 3, which examines factors and multiples of whole numbers. That doesn't sound very specific, but the point essentially in our first two parts in 3.1 are determining prime numbers and prime factors, greatest common factors, and least common multiples. These two outcomes of greatest common factors and least common multiples will ultimately be our goal. To start things off, I've mentioned the word prime factors and prime numbers, and this becomes our first definition. Prime numbers are numbers that can be divided only by 1 and itself. So this is a very specific set of numbers that begin with a 2, and then a 3, and then a 5, and then a 7, and you could ask yourself, what's next? Well, how about the number 8? Well, because 8 can be divided by 1 and itself, but also 2 and 4 both make 8, it doesn't get added to the list. The number 9, well, 1 and 9 create 9, and 3 and 3 make 9, so it doesn't get added to the list. The next number is 11. There's only one way to make 11. 1 times 11. 13, 17, 19, and so on. The list never ends, and a lot of people have spent their entire math careers trying to find patterns in prime numbers. The next definition for prime factorization involves breaking a number down into its parts. At its core, what are a number's parts? So we'll write this down as breaking a number into its factors. Breaking a number into its factors, which are primes. So this is not a textbook definition, but prime numbers are essentially numbers that can be divided by only 1 in itself, and a prime factorization is breaking a number down into all of its parts, which are primes, which we can look at in our first example, example 1, the number 24. The question asks us to write the prime factorization of 24 using a factor tree. So what are all the different parts that make up a 24? And you might say, 24 and 2, 6 and 4, but this could be broken down even further. So we're going to do something called a factor tree. 24 can be broken down into two numbers, and there's lots of choice. I'll start with a 3 and an 8. The number 8, though, can go a little bit further, maybe a 4 and a 2, and the 4 could go a little bit further into a 2 and a 2, and there's no further we can get because 3, 2, 2, and 2 are all prime. So this is a prime breakdown of the number 24. So we could say that the number 24 is a creation of 2 times 2 times 2 times 3. Or we could even say 2 cubed times 3. And this is what makes 24, and this is the only way to break down the number 24 into all of its parts. So, a couple to try. Feel free to pause the video and see if you can break down the number 162. Remember, there is more than one way to break down a number, just like I could have broken the 24 into a 4 and a 6 or a 12 and a 2 to start. Ultimately, we all arrive at the same answer in the end. Feel free to pause the video, otherwise, I'll begin. A 162 could be broken up into a 2 and something because I do see that that is an even number. So I'm going to divide it into an 81 and a 2, and some people might need to use their calculator and say 162 divided by 2. Otherwise, the 81 can be broken into a 9 and a 9, and therefore a 3 and a 3, 3 and a 3. And we'll circle a number every time we see that it's prime so that we can rewrite a final answer of 162 is a 2 by 3 by 3 by 3 by 3. You can always double check your work by multiplying them back together to see if you arrive back at your original question. to write it as a product of primes in power form, we could say it is a 2 times a 3 to the power of 4. And both of these are excellent ways of writing this. And lastly, 3300. You might be unsure of where to start, but I do see that it has a 100 in it, so we might try to take out a 100. You might try to find a bigger number, a smaller number, just to pick a random number. Let's take out a 300. And this one I know works because if I take 3300 divided by 300, I end up with 11, which is actually already prime. 300 breaks up into a 3 and a 100, which I can circle a 3, a 10 and a 10, a 2 and a 5, and another 2 and a 5. All are prime. In the end, we have a 3300, which is made up of a 2, a 2, a 3, a 5, and an 11. The ability to break numbers down into their primes is a very powerful tool that we will examine on the next page. Greatest common factors becomes our next task, and this is one of the 2 things that I mentioned at the beginning of the lesson. The greatest common factor of 2 numbers is the greatest factor that both have in common. So, looking at all the factors of 2 numbers, what do they have in common that is the largest? So, for example 2, we have the greatest common factor of 24 and 16. We're going to examine this in 2 different methods. For simpler numbers, we might look at all the different ways to make 24, and some people will be much more skilled at this than others. So what numbers could recreate 24? Well, a 1 times a 24 could make 24, a 2 times a 12, a 3 times an 8, a 4 times a 6, and that is it. For the number 16, we have a 1 and a 16, a 2 and an 8, a 4 and a 4. To determine this, you might have to take your original number and divide it by 1, by 2, by 3, by 4, by 5, and so on, hoping for whole numbers. The greatest common factor is examining in the list the largest number that they have in common. And they don't have anything other than an 8 and a 4 and a 2. 8 becomes our greatest common factor. Now this works for smaller numbers, but when the numbers become larger or we have multiple numbers, we might need a more powerful process. So in example 3, we have 3 numbers, 28, 56, and 42, and even though there are multiple ways to approach these questions, we're going to examine this using our factor trees. So for longer questions, or multiple numbers, we're going to first write the prime factorization of each number. You're more than welcome to do a factor tree on the side, but I'll write our more simplified version now. For the number 28, it could be broken up using a factor tree into a 2 by 2 by 7. The number 56, we could break up using the similar approach as before into a 2 by 2 by 2 by 7. And for the number 42, we could break it into a 2 by 3 by 7. Now, our second step, after we write the prime factorization of each numbers, is to circle the numbers that appear in each prime factorization. I see a 2. I don't see another 2 that they can all share, but I do see a 7 that they all share. And the product of what's in common is our greatest common factor. So a 2 times a 7 is our greatest common factor. Though this approach can feel more complex, it is a much more powerful way of getting our answer. For try 3, we have determined the greatest common factor of, again, 2 larger numbers. And let's try this with this approach. Feel free to pause the video. Otherwise, we are looking for our prime factorization of 63. So on the side, you're breaking a 63 down into its parts, arriving at a 3 by 3 by 3. That's for the 27. For the 63, we're breaking this into maybe a 7 and a 9, and ultimately a 3 by 3 by 7. And asking what do they have in common? They each have a 3, and they each have another 3. Unfortunately, that is it. So the greatest common factor is a 3 by 3, which in this case is a 9. And this should sort of make sense, because if we take the number 27 and divide it by 9, we get a whole number. If we take a 63 and divide it by 9, we get a whole number. This is the largest number that can do that. As we flip it over, we have 2 more examples to simply try. And again, you're more than welcome to pause the video and give it an attempt. Otherwise, we'll work out our solutions. So determine the greatest common factor of 138 and 192. So 138, if we break this up into its prime factorization, we're left with a 2 by 3 by, yes, a 23. That number is prime. For the number 192, we could break it into a 2 by 2 by 2 by 2 by 2 by 2 by 3. Which then we can ask, what do they have in common? A 2, a 3, and that is it. So for this question, even though there was lots of 2's, all they share is a 2 by 3 or a 6. And lastly, a number that is quite large, greatest common factor. If you break them down into all their parts, we have a 100, which is created from a 2 by 5 by 5 by another 2. And the number 25 is a 5 by 5. And the number 330 is a creation of a 2 by 3 by 5 by an 11. And circling what they have in common looks to be not a 2. They don't have a 3. They do have a 5. And unfortunately, again, that is it. So the greatest common factor is a 5. This is examining 2 specific outcomes: prime factorizations using factor trees, as well as a more powerful process of determining the greatest common factor. In the next video, we examine the lowest common multiple, which begins in a similar way, but ends with a different process.